what we're going to do today is we are going to go ahead and do quadratic regressions that model data. And how we're going to do that is we're going to do it through Desmos because not everybody has access to a graphing calculator. So essentially what this is we're going to get data sets, and then we're going to find curves that best to our ability fit that data. And so it's an approximation tool. And realistically, this is kind of where a lot of the math gets used, gets used as an estimation tool. Okay. So NASA can create weightless environments by flying a plane in a parabolic paths. The table shows the height in feet of a plane t seconds after starting a flight path. After 20.8 seconds, the passengers begin to experience a weightless environment. Write and evaluate a function approximate to the height at which this occurs. So then what we'll do is we'll go ahead and pull up Desmos. Okay, and what we can do is we want to type that data into Desmos here so they have access to it. So if you start typing the word table, it will give you a table. And for our x values, we want 10, 15, 20, 25, 30, 35, 40. Okay. And then for the y values, and I'm just taking this right off the table from our notes, so if you have that out, that's where we can get it from. 26,900, 29,025, 3,600, 31,625, 32,100, 32,025, and 31,400. Okay. The problem is, my x and my y axis doesn't really fit this data because my data goes all the way to the 40s and x and then the several thousand, so we want to adjust that. So if you hit this gear here, we can go adjust our graph. And let's go ahead and look from 0 to 40. Okay. And so as you can see here, it's adjusted our graph. And actually, instead of 40, I want to go all the way to 50. Okay, for the y-axis, as I look here, my numbers range from like 26,000 all the way to 32,000. So let's go a little bit above and a little bit below that. And I want to adjust it, and let's say 25,000 would be my minimum. And then here we'll go ahead and say like 35,000. Okay. Commas there. Okay, that's important to know. Okay, so as you can see there, I was having errors doing that. If you have commas in your numbers for the axes, for some reason it doesn't work. So go ahead and numbers without commas. Okay, as you can see here, our data does seem to form a bit of a parabola, or at least part of it. It appears to follow that. So what we want to do is we want to make an estimation of this. So what we can do is we can go ahead and hit Y1 here. Or we can go into 2, and if you hit y and then the number 1, okay, this is going to create a function for you, saying it's going to be y1. And what that's going to be equal to is, instead of equals, you want to hit the tilde button. It's typically the button immediately to your left of the 1 key. And then what we want to do is we want to type a function in this form, a, and then x1, squared. Okay, and then squared can be done by shift 6 and then 2 plus b times x1, and again because x1 is our x variable, and then plus c. So as you can see, this black line here is a very, very good estimator of this function. Okay, and what is our function? Our function, it gives you A, B, and C values down here, if you can go ahead and see where my mouse is hovering over. Okay, and what that means is that's my A value, B value, and C value. So that means my function would be equal to y equals negative 11x squared plus 700x plus 21,000. And now you can see that red line here, that is exactly what my curve is. This r squared is how good of an estimation it is. The closer to 1, the better it is. So this is right on 1, so that means it's actually a perfect fit. So that is our function. Okay. And then it says it wants to approximate the height at which this occurs. So after 20.8 seconds. Okay, so what we can actually do is we can call this function f of x. Okay, and so then if we call this, and this is just function notation, which we've had experience before, if this is my function notation, function named f, variable is x, what I can do is I can just go f of, and then I want to know what the value is when it's 20.8, because that's the time at which, if you read here, after 20.8 seconds, passengers begin to experience a weightless environment. So if I go f of 20.8, it says at about 30,800.96 feet. It gives you the result there. So there's two things that you're going to need to be able to take away from this, and that is how to create the table and get the equation. Okay, the equation is always going to be in this form here, and then you get what A, B, and C are for this. Okay, so let's go ahead and try this all again, but with a different problem. All right, so this is C. Okay, so I think it's best if you try this on your own and then check in with me when you're done. So I'm assuming that you've already paused the video and you're here to see how you have done on this problem. Okay, and this table here shows the estimated profits, Y, in dollars for a concert when the charge is X dollars per ticket. So as my ticket prices increase, it maximizes my money, but then after a while it's too expensive and your profits go down. Write and evaluate a function to determine what the charge per ticket should be to maximize the profit. Okay, so we're going to go into Desmos. Okay, and the first thing we want to do is type our table. So you just start typing the words table and it will pop up. My X values are 2, 5, 8, 11, 14, and 17. Okay, when my ticket price is $2, my profit is $2,600. When my ticket price is 5, it's 65. It's 8,600, 8,900, 7,400, and then 4,100. Okay, but again, if you look from the previous problem, my X and Y values are way off for this. So let's go into our gear and let's change to X. So it looks like my X's go from about 2 to 17. So let's start it at 0 and go all the way to, let's say, 20. All right, and then the Y's are way in the tens of thousands. Okay, and so what we want to do is we want to change this. So it looks like it's, my lowest is 2,600 and my highest is about 9,000. So let's just go from 2,000 to, let's say, 10,000, just to be safe. Okay. And then as you can see here, we do see our dots. It appears as though it follows generally some sort of parabolic path. So we want to go ahead and use our regression. So you're going to hit Y then 1 for our Y sub 1, our Y sub 1 element. Okay, and then if you hit that tilde button, which is shift, and then the button right next to the 1 to the left of it. And then we want it in the form A, x1 squared plus B times x1, and then plus C. Okay, so again, it looks like it's a pretty good curve. Okay, and it looks like it fits it perfectly. In fact, as you can see, my R squared statistic is exactly a 1, meaning that this is a perfect fit. Okay, so that means my function would be f of x is equal to negative 100x squared plus 2,000x and then minus 1,000. So this green line is our perfectly fit curve. Okay, and then what I want to do is I want to determine what I should charge for a ticket so that I maximize my profit. So based on our other lessons, we know parabolas have maximum and minimums. So if we're trying to maximize my profit, which is this Y value, we want to find the ticket price X that goes ahead and maximizes that. So actually, if you click on your line, okay, let's go ahead and get rid of this now that we already have our curve. If you click on my line and hold the cursor, you can just drag it and you can kind of see. And the maximum or minimum point, as you can see, is always this gray dot, okay, or it will be at the top or the bottom. So it looks like here, this is my maximum point. So what does this mean? At 10 comma 9,000 means my x is 10, 9,000 is y. That means at a ticket price of $10, my profits are maximized at $9,000. And that's how you find the maximum. Okay, let's go ahead and do the same thing basically with number 4. Okay, so we're moving on to number 4 now. Okay. This table shows fuel efficiencies of a vehicle at different speeds. Write a function that models this data. Use the data to approximate the optimal driving speed. Okay. So again, we want to go into Desmos and we need our table here. Okay, looks like our table's already created. I'm just going to X out and just go ahead and type table again. Okay, it looks like my X values are at 20, 24, 30, 36, 40, 45, 50, 56, 60, and 70. And then the miles per gallon based on those speeds are 14.5, 17.5, 21.2, 23.7, 25.2, 25.8, 25.8 again, 25.1, 24.0, and then 19.5. Okay. And again, we have the same issue as we had every time. This is in the thousands, this is in the X's. We want to change this. So I want to get from like 20 to 70. So let's go change our X's. So I'm going to click in here, and I get a minimum of 20, max of 70. Let's go 10 to 80, just so we have a very clear picture of everything that's going on. Looks like my X or my Y values are much more lower. Looks like from 14 to like 25. So let's just be safe on the safe side. Let's go ahead and just go 10 to 30, I think is appropriate. Okay, and then I can click out. And now I can see this is clearly some sort of parabolic path, meaning that a quadratic regression is appropriate for this type of scenario. Okay, so we're going to hit y1, and then is approximately a 1x squared plus b times x1 plus c. Okay, so now we can see this one that my R statistic is not quite 1. It's a little bit less. As you can see, it doesn't go perfectly through every dot. But this is actually the power is that of these regressions is that it is truly just an estimation or an approximation tool. In real life, data is not going to always fit a perfect parabola if it's a function of a quadratic equation. But that doesn't mean that a quadratic equation can't represent it accurately. So in this one, this is very close to 1, my R squared statistic, meaning that this is a very, very, very good fit. Is it a perfect fit? No, but is it a very good one? Yes. So as you can see, my parameters here, my A, B, and C value for A, B, and C are not quite perfect. So what we want to do is round to the nearest thousandth, and we will call that good. So we're going to say my function f of x is equal to negative 0.014x squared plus 1 times 1.366x minus 7.144. Okay, and as you can see, it's not going to be perfect. It's going to be a little bit off because we're not typing these whole numbers in there. Okay, so this black curve is going to be our estimation. Okay, and again, we're having all of these values rounded to the nearest thousandth. Okay, so what does the question ask? It wants to use the data to approximate the optimal driving speed. So this is my miles per hour in my car, and this is my speed. So at what speed do we want to go ahead and maximize my fuel efficiency? So if we look at our curve here, again, we're to maximizing the fuel efficiency, we're looking for the maximum value. And on Desmos, it's very nice. It gives you this. Okay, so based on our data, we can assume that at 48.786 miles per hour, so about 49 miles per hour, this table or these vehicles miles per gallon is maximized at about 26.177. So again, my x value, speed, about 49 miles per hour, maximizes my car at about 26.177 miles per gallon. Okay, so when you're doing these problems on paper, you should be writing this equation down, and then you should also be answering the question just using a sentence. Okay, one more. Okay, the table shows the results of an experiment testing the maximum weights, y, which is in tons, supported by ice x inches thick. Write a function that models the data. How much weight can be supported by ice that is 22 inches thick? Okay, so again, we need to go ahead and create our table and put our data into it. So we're just going to type the words table. Okay, and it looks like we have x is inches of the thickness of the ice in inches. So we have 12 inches and 14, 15, 18, 20, 24, 27. Okay, and then we also have the weight in tons that it can hold based on that. So 3.4, 7.6, 10.0, 18.3, 25.0, 40.6, and 54.3. Again, we need to change the range of our window. Okay, so what we are going to do is we're going to hit graph, and we need to get in 12 and 27 in. So let's go ahead and go 10 to 30, I think is appropriate for the x's. And for the y's, I need to get 3 to 54. So let's just go from 0 to, let's say, 60, just to be safe. Okay, now this looks like a different part of a curve, right? So this one appears to be going up, but if you can imagine this being a symmetric thing here, it might shoot back up the other direction if you follow the track of my mouse. This could easily be a parabola, so, or at least part of a parabola. So let's go ahead and get our regression. So y1 is approximately x1, or a times x1 squared, plus b times x1 plus c. And as you can see, this is a very, very good fit. It goes through all of our dots pretty cleanly. Furthermore, my R statistic is 1. My R squared statistic is 1. Okay, so what we want to do is we want to go ahead and approximate this. Again, when you have all these decimals, just go to the nearest thousandth. I'm very much okay with that. We understand that there's going to be some error when it comes to these problems. Okay, so is equal to, and if I want to round this, if I want to round 0.998, that 8 would round the 9 up to 10, 10. Okay, so this is going to end up being 0.010x squared minus 0.498. Okay, this 7 would round that other 7 up to an 8. X, and then minus 5.007. I don't see it popping up. Did I type something in wrong? As I zoom out, I can see that's not a very good fit at all. Oh, I see why. I rounded incorrectly. Okay, so this is going to happen to, I'm sure, many of you at some point. I accidentally rounded this up to the wrong decimal place, and it should be 100. Okay, so this 9 would get rounded up, which would round this 09 up to 10. Okay. Anyway, so this is my curve, and my question is, how much weight? So we should be writing this equation down on our paper. And the question being asked is how much weight can be supported by ice that is 22 inches thick? So we need to think about x variable is my the thickness of my ice. So here it looks like, right about here is where we're expecting, somewhere between 40 and 20. We can be very precise. We can say, I want to know what f of 22 is, saying what is the function value when x is 22. And it looks like it's 32.437. So what does that mean? That means when x is 22, when the ice is 22 inches thick, it can support weight of 32.437 tons of weight. Okay, so for those who do not have a graphing calculator available, this method is how you can do your quadratic regressions for your test review and anything else you are doing. Otherwise, I will see you next time for the next lesson.